We are looking at odds, which is a specific type of probability. It is continuing with the idea of probability being what you want over all possibilities. But now when we're dealing with odds, we write it as a ratio. And really the first good question that should be asked is why? Why would we bother doing odds when we already have probability and we can show something as a % chance of it happening? And odds is used all over the place. Almost every casino, any kind of sports betting goes and shows their results in odds. You can go and place a bet on the odds of a certain team winning a championship. There are times where, like, if celebrities are having a baby, people will place odds on what the name of the baby will be, the gender, that kind of thing. There's lots of craziness that goes with betting and with odds. But why use it? Why say the odds of a team winning are 1 to 50? Why not just put it as a %? The Tim Hortons Roll Up the Rim to Win contest, Princess Margaret's Cash for Cancer lottery are probably two of the best examples of this. And the short answer is that odds get used in probability because they sound better and it's more manipulative. So if you're running a contest, you want people to buy lottery tickets, you want them to buy more cups of coffee so that they participate. And Tim Hortons is a great example of it. It says right on their cups, right on their posters, that the odds are 1 in 9. And notice that is not a probability. If it was a probability, it would be 1 divided by 9, and it would show as a %. 1 in 9, or odds of 1 to 9, mean for every 10 times you play, 1 of them wins and 9 lose. So that's the key here. So why say 1 to 9 instead of probability? Think for a second, what would the probability be? It would say that if you're participating in the Tim Hortons Roll Up the Rim to Win contest, you have a 10% chance of winning. And the reality is that we as people are impacted by that. We know 10% is a low odd, low probability, and it doesn't sound that great. 1 in 9 sounds better. It sounds better than 1 in 10, and 1 in 10 is what 10% is. So that's it. So you have this whole little subtopic in probability to learn called odds, just because the gaming, lottery, gambling industry goes and uses odds because it sounds better. And the other thing that these different contests do, like Tim Hortons, is to flood the prizes with all these little inexpensive prizes so that the odds actually sound better. So they can legally say that there's 1 to 9 odds of winning, because if you buy 10 cups, you should buy 1. So you should win 1, and you will likely lose 9 within that. But that's of small prizes, like another free coffee. You start looking at the actual prizes, even something small like a Tim's card, you're looking at an odd of 1 in 3,275. And then the grand prizes, you're into the 1 to the 16 millions. Okay, so formal definitions of odds. Earlier, we looked at this idea of a complement of an event. So you have the probability of it happening and the probability of it not happening. And now you see why that is so important. So for the most simple kind of an event, rolling an odd number on a die. There are 6 numbers on a die, so 1, 3, and 5 are odd. Of course, 2, 4, and 6 are even. So the probability of event A, which is rolling an odd number, is 3 over 6, which equals a half. The complement is the opposite. So it's the probability that event A does not happen. Here we have the complement of A just being an even number, because of course half are odd and half are even. So the probability of event A happening is a half. Here are odd numbers. The probability of event A not happening is also a half. And this is a good visual reminder that all probability situations can be represented by a Venn diagram, and the total sample size is 100%. So what's some of the language that goes with odds here? Odds is just another way of showing probability, but it also has a confidence value that's there because it shows you the ratio of it happening to it not happening. So it's best to use odds when the probability of an event A versus its complement, A not happening, is really important. And the examples of this are ones that I've already shown, but it's why you see it in contest, lottery, any kind of win versus loss ratio, because the importance of it happening versus it not happening is really what the focus is. So something like the probability of, you randomly pulling a pen out of your pencil case, the probability of it being a red pen, that's not really interesting as odds. You just want to know the chance of you actually grabbing that red pen. But it's things where the chance of you losing money is as important is when it tends to get shown in odds. Formal formula here. I am going to go through the theory and the formula, but the reality is that you're not going to be required to reproduce this. Odds can just be done in a common sense kind of way too. But the formal formula is the probability of event A is equal to the number of ways event A can happen over the total number, which is the sample space. So we traditionally will use an S here to go and show that sample space, just so it's the same language as Venn diagrams. So now there's two little definitions that go with it. The odds in favor of event A happening are the probability of A to the ratio of the probability of A not happening. But because odds work in both directions, you can also have the odds against. So when you hear this in terms of sports wins, you can bet on the odds in favor of a team winning, but you can also bet on the odds against a team winning. So the general rule is that you reduce the probabilities, you reduce the fraction, and your final odds answer will be a simplest ratio possible. You will never have a fraction or a percent when you're showing odds. And again, think of where you've seen this in real life. If you've seen it on a contest, if you've seen it in different kind of situations where there's some betting that's happening, it's always written as odds of 3 to 1 or odds of 1 in 10. You never go and have it as a percent or as a fraction. Okay, theory aside, what do you practically have to be able to do? Here is a guaranteed kind of question that would be on a quiz or test. I give you a situation where theoretical probability is very straightforward to calculate. You just do the probability and then you write your final answer as odds. So I want to be very clear that odds is not a new type of probability. It's still just probability, exact same process, but you write the final answer in terms of a ratio that show the probability of it happening versus the probability of it not happening. So 2 steps. Step 1, do exactly what you did in the previous topic. Calculate the probability. So the probability of a king is 4 over 52. Where did I get those numbers from? In a deck of cards, there are 4 kings and there's 52 cards total. So that's my sample size. What I want is a king, that's in the numerator, over the denominator of the sample size, which is 52. If you're not that familiar with card games, not a problem. Go and print off or find just a picture of a deck of cards. You'll see all 52 written out there. It makes it really easy to do these kind of questions because you can see, for example, that there are probability of a heart is a quarter, probability of a king is 1 over 13, probability of face cards, there's 12 cards that have a face on it, so that would be 12 over 52, which equals 3 over 13, that kind of thing. Okay, getting back to this question, you have a probability of a king is just 1 over 13. That means the probability of not getting a king is, sorry, I'll go back here. Probability of not getting a king is 48 over 52, which is 12 over 13. So now you do the actual final step, which is odds. Now you go and write them by only writing the numerators, and you get a final answer of 1 over 12. Because if I took 1 over 13 to a ratio of 12 over 13, I can cancel out the denominators by just multiplying both sides by 13. So why bother? It just clutters up the ratio. So that's it. If you are asked what are the odds in favor of drawing a king, you simply do the probability of it happening, the probability of it not happening, and then you write the final answer out. If you're able to look at this question and just see the answer, that's great. Write down the answer. It's really only the two-step questions where sometimes you need to do a little bit of work in between. Another example, what are the odds against drawing a diamond? Remember, with probability and odds, we have two different things we look at here: the odds in favor of it happening or the odds against it happening. And so in this case, it's the exact same process. I'm just going to write the final answer in a different way. So step one, probability. Probability of a diamond is 13 diamonds divided by 52 cards, but we can reduce that down to a quarter because a quarter of the deck of cards are diamonds. So probability of a diamond is 1/4, which means the probability of not a diamond, which is really just the probability of hearts, clubs, or spades, is 3/4. Now we write out that the odds against, using only the numerators, the odds against getting a diamond are 3-1. What if the question had said, what are the odds in favor of getting a diamond? Same process. Final answer would be odds in favor of getting a diamond are 1-3. We can go in the opposite way too. So what can be a little bit more challenging is when I give you an odd situation and then you need to back up and get the probability. Again, I'll show a formula on the next screen, but I think common sense is the way to go here. If the odds in favor of Shirley having lost her handouts are 8-1, what's the probability that she lost them? This means that for every 9 times, she loses them 8 times and has them 1 time. Where did that 9 come from? 8 + 1. Your sample size here is 9. So if you were to break the odds up into probability, you would have an 8/9 and a 1/9. And so that's where we go to. So final answer, probability that she lost them is 8/9. If you're asked to show it as a percent, you would just take 8 divided by 9 times 100 and get 88.9%. Here is the general formula. Again, I use this because it just helps. I can memorize formulas and it helps, but you can do this in a common sense kind of way too. So if the odds in favor of A happening are H/K, so that could be 1/4 or 1/6 or whatever it is, then the probability of event A happening are H/H + K. What's happening with this whole H + K thing? It's just like going back here. It's just adding the two numbers, 8 and 1. So the whole idea of the H + K is just to figure out your sample size. So what are all possibilities? And all possibilities are the number of ways the event happens and the number of ways the event does not happen. So as an example, if the odds in favor of passing this course is 5-2, what is the probability of passing? I think the odds of passing at this point are much better. Most people have dropped out of management by this point if they don't think they're going to pass. But the odds in favor of passing of 5-2 mean that for every 7 students that are there, 5 will pass and 2 will likely fail. And so that is, how do we convert that to probability? 5/7. Take the 5 plus the 2, add them together. That's your new sample size. So the probability of passing is 5/7 or 71.4%. The probability of failing is 2/7. As a final note here, so that is all that's involved with odds. It's like a 2-step question where you still just do probability and then write your final answer as an odds ratio. The difficulty that comes in with some of these questions is that probability questions are easier to do if they're more complex or involve a couple of steps. When you're given the ratio, it's very hard to do multiple questions, like the chance of winning a contest on the first time or second time or third time you play it. Or in this case, it says, yeah, it's fine that there's a 1-9 ratio of winning a prize at Tim Hortons contest, but what's the probability or what are the odds of winning it twice in a row? You can't take that 1-9 ratio and easily do something to convert it to twice in a row or 1 of 3 times or at least once or any of those kind of questions we tend to do in data management. So what's the process? convert to probability, just convert it to probability and go from there. So if the odds of a win are 1 to 9, your probability of a win is 1 over 10 or 10%. Now that's something that we can easily work with, because your probability of 2 wins is 1 over 10 times 1 over 10. If we are winning 2 times in a row, that's an and situation. It's like asking what's the probability of winning once and winning the second time. So I take my individual probabilities of 1 over 10 and 1 over 10, and I multiply them to get 1 over 100 or 1%. Now I can go backwards again and write it in terms of odds. So the odds in favor of winning twice in a row are 1 to 99. Notice your original question with an odds of 1 to 9. There's no one step there where we can just do something or multiply it to immediately get that 1 to 99. So it's important to go back to the probability and work through there. As an aside, what would the answer be here if it was what's your probability of winning on the first cup or the second cup? You follow the exact same process. The only difference is that this multiplication symbol becomes an addition symbol. So with the or situation, it would be 1 over 10 plus 1 over 10, which is 2 over 10, which reduces to 1 over 5. And then your final answer would be a 1 to 4 ratio. And that's a really good distinction to show how hard it is to win any kind of contest twice in a row. Whereas the more times you play, the more likely you will be to win something, to win one or the other time, because the probabilities decrease as the trials increase. So that's odds. That's all we're looking at here, taking your probability and going and showing that instead as a ratio.